Hello everyone, here is Samuel from Sesfart Labs, and today we are going to get started on a KiCad project. So this will be a small part of a bigger project that we're going to work on. And today we are going to introduce you KiCad, which is the PCB designing software that I use. There's Ultimate Designer also, but we mostly use KiCad because it's open source and it's free. And in this project we are going to have, let me just open Notepad. So we're gonna have STM32 F0 MCU, and we are going to make a dev board with RS-485 communication and also some pinouts, basic pinouts. That's what we want. We want our voltage input to be from a USB-C, so we are going to use any voltage regulator. So on the board, so we need a voltage regulator part. We need also a LED as a MCU. We need a LED so that we can program it. We can write our first code like a blinking code. So we need a LED. And also we will need we'll need one connector for the programming. So that's how we are going to follow up the sequence, and pin headers also for the pinouts that we have. Okay, so since we are using STM32, we are going to open Studio MX. I already have a project in it. So this is the STM32 configuration software where you can configure your MCU. Yes, so we have here. So here I already configured the STM32. So basically when you select your MCU, which ours is the STM32 F0, 42, F6. So this one will get the pinouts, and when you click in one of them you will get to see all the configurations that you can put for this specific pin. Therefore I have configured most of the pins as GPIOs, but you can see here we have I2C, and we also have CAN communication in this. So we can use CAN RX, and I might find CAN TX somewhere here in the connectivity. In this board you need P8. Okay, so here I'll have to, if I want to use CAN, then I need to disable P812. P812, where is P812? Okay, since we don't have P812 here on this specific MCU, we cannot have CAN. Therefore I'll just enable my serial debug, which the line that we're going to use to program it. So this is the basic configuration. We have pinouts. We have to configure for RS-485, so we'll go for UART. and we'll just put hardware flow control so that we don't need to do it manually. And we go for asynchronous, and you just enable that, and you'll get these 3 pins enabled, which is this one is transmit, receive, and enable receive or enable transmit. So this is the pin for that. Along with, we are going for the RS-485 transceiver. We are going to be using this transceiver here, which is done by Analog Devices, the RS-485 or RS-422 transceiver. Once you open KiCad, this is the page that you are faced off. This is what the latest KiCad version, and you can find it in their official website. And here we have file. So whenever you open this, you need to go to file, to new project, and start a project. I already started a project, so I won't need to do that. And then as soon as you start a project, you'll be faced with these two, which is this is your PCB layout and this is your schematics. Today we are just going to get with the schematics, and then we'll fast forward to the PCB on the next episode. So in the schematics, yours most likely to be white. I just have my team to be black like this because it doesn't sting my eyes. So we have our MCU, which is STM32 F402 F042. So just find that. It will take some time to load this. So let's just search STM32 F04 to this. Not this one. We have F042 F6P. F6. Yes, which is this one. So just gonna place it over here. And we have here our MCU. So what I like to do first is place all the major components in the PCB. So if you want to put any symbol, you can click A on a keyboard, or you can just come here and place symbols. And the next one is max. Which max we are using, just to make sure we get the right one. We have max 3483. And we just place this one over here. So these are our major components. Now we need a voltage regulator. Just put a voltage regulator, and we can go with the simplest one, is AMS 1117 3.3, which is a 1 ampere rated voltage regulator. And let's just keep it over here. So now what I'm gonna do is work out on the pin outs. So basically we have most of our pins. I'll first name the pins that are connected to our RS-485, which were PA1, PA2, and PA3. So just get those ones. You can right click on your mouse and you can get here pin header functions. So you can just name them like this. So we have here our 3 pins, and you can just basically again right click after selecting all 3 of them. Sorry. And you go for NAT labels. So what are NAT labels? NAT labels are basically You don't need to wire everything like traces like this. You can just label them individually and then you copy them and just paste it over here, and that will be it. So I'll just keep it here, and I also like to make boxes separating everything. So we have in this area our MCU. Just give it a name. So here we have our STM32 MCU. And after we name these guys, we are going to find out, we are going to make this one, which is just a normal pin, we are going to give it built-in LED. Just put the label, double click it, just name it B underscore LED, and we are going to connect this also to a pin so that it won't be a unused pin. And now we have here everything else is just normal GPIO besides the PA14 and PA13, so we just do that as well. Which our system serial wire plug and serial wire IO. This is for programming. You don't need to put it outside, but I normally like to do that. And this one is just keep normal labels. And we'll fix here as we don't have BA11, BA12, so we call it BA9. Same applied for this guys, there's normal GPIOs. I'll just adjust this a little bit like this. Don't need all that space. And in this specific we won't use any crystal, therefore we are not putting any crystal isolator. So here we have our reset pin, and this is analog voltage input, analog reference voltage input, and we have normal analog, and we have here our ground. So our ground, we just click P, JND, and then you get your ground. And you can get to know all these shortcuts by driving, just putting your cursor above any of these. You see, for placing symbols you can get A, for placing power symbols you can get E, therefore I'm doing that. And for these guys we'll just put, so for this PCB we don't need a specific voltage regulator for the voltage reference, therefore we're just going to put a filter array for this guy. So we have the decoupling capacitor for the VDA, just put C over here, and then DC, and just give it 100 NF, and the footprint I'll put 0402, capacitor metric, that'll be it. And then I can just copy the same capacitor for anywhere I need for the same purpose. So here we put 10 NF, actually should be informed closer to this guy, 100 NF, and then 1 UF, So basically just trying to get the most stable voltage on the analog input. You can just join these guys, join this guy, and if you want to have a look on the datasheet, you can get access of the datasheet of this MCU. I won't get into that because it's gonna take a lot of time to explain everything in the datasheet, but I can make a specific video explaining how to go through the datasheet of the specific MCU for better clarity. So now we have here our capacitors non-polarized, and we need supply. We need 3.3 for these guys because our MCU works on 3.3 volts. So just get click B, use a 3.3 volt label, and we just power here. Just copy the same one, pass it over here, and power here. And we need ground, so we can short our grounds together. That doesn't affect anything. You can just leave it open also and just put two individual ground labels. So just copy from here, put it here also. So we have our power of this MCU all done. Now we'll go to the RS-485, the transceiver. So for the RS-485, we know that A and B lines needs a 120 ohm resistor in parallel. So we'll just put that. Let's go for an put it over here. Can connect it like this, and you need the connector for the output. We'll do that later. This would be a 120 R. Output 06, and we can do 0402 as well actually. And this 0402 is just basically sizes of this SMD component. Then we have VSCC and GND here. So we're just gonna copy one of our decoupling capacitors so that it will be, you can do it faster instead of going through the same process. Just ensure that you want to use that specific, the same footprint that you are using. So if you want to change it, you can just come and change over here, but I don't want to change it, and the value I want it to remain same. And we'll also copy our ground. For the decoupling capacitor, and also we put one over here for the ground of the transceiver. And then we'll copy these three guys here. So here we have a driver input and receiver output. So receiver is our RX, TX is our driver input, and here we have receive enable, drive enable. So we can short these two and connect, because one of them, when this pin goes high, one of them is enabled, and one is enabled when the pin goes low. So we can short them together. I could not find it in that specific datasheet, but it should be there. Here is the information, so you can see what happens. And we have a table also that explains exactly what happens on in which state here. Transmitting, receiving, you can see. Okay, so that is also it for this guy. So let's just make a box for him as well. Let's just put it somewhere in the middle and put a max, input max. Actually, I'll just put RS-485 grounds, TX, RX, RX, didn't name it anything. So we have the MCU configuration done, we have the RS-485 done. Now we get to the voltage regulator. So in the voltage regulator, we just got capacitor again. We can just copy it from here. I like having two capacitors in the input and two capacitors at the output with different values, like this. This is voltage input, this is voltage output. Then we can short all the grounds together and just use it. This guy over here, power this. We get the 3.3 and put it over here, and we change this capacitor for a 10 UF, the bulk capacitor, and we'll find a bigger footprint, 0.8. You might find it in 0.6 also, so just keep it 0.6. And for this one you keep 1 UF, and you'll keep the same footprint. Same I'll do at the input. Actually just copy this one, delete, and here we'll change the value to 1 UF. So we are done with the voltage regulation as well. Let's just make a box for him. Voltage. And put it over here, and we can give a power label V in. Actually just be VCC. Yes. So we have it mostly done. Now we need to put some connectors. So for the RS-485, since it's a specific board, I would like to keep it either in the breadboard. Since this is a small board, I'll make it in the breadboard, but on the future versions we'll remove it from breadboard, because this same base will be used for a actual project. So for now I'll keep everything breadboard. So we have two connectors for this guy, actually three, one of them is ground. So just search here connector, go for the 3 pin, come over here, you can rotate this. You don't need to change the name specifically. So I like to keep everything symmetric often, so don't bother. You don't need to bother doing it specifically like this, and you get ground here. So and I prefer to give the footprint right away, so just find here some pin headers of 2.54 pitch. So we have 1 mm pin header, SMD, we need true hole, 2.54, not SMD, true hole. 3 pin one, vertical, yes, and then we'll put a LED. Forgot the LED. Just keep a simple LED. Here we are cathode, here we are anode. So just connect the resistor in line. I normally keep. Let's just copy this one. Actually, since the footprint is gonna be same, and now just change the value to 1K. And we'll just put here the built-in LED, and here we connect our ground and make this a green LED. Green LED. Keep the footprint small also. 0402 metric, and we'll copy the same LED. We just copy it and put it over here. That will be our power indication LED. Just remove this. You can simply just drag this one to here. So this is our power indication. Whenever 3.3 is available, it will right away light up, and you can make this a red LED. So LED is done. So now we are going to make the pinouts. The reset, I will come back to it at the end. You don't necessarily need to route it, but if you want the reset button, you're going to put it. So for this, we are going to have 1, 2, 3, 4. 1 second. 4, 5, 6, 7, 8, 9, 10, 11 pins. So if I try to divide that to even numbers, oh, we have to 12 for our VCC, 13 for the 2.3, and 14 for the ground. Okay, so we'll just put some connectors here. I'll just make another box. And now find some connectors. I said 14 for the ground, and I'll make it 16 because we have these three also. So just make it 16, and you divide it by 2 because we have 8 in one in each side. So keep 8. So 8 in one side, and let me just put the footprint for them. 2.54, and then we look for the through hole. Need 8 of them, vertical. Just copy this one, put it over here, and rotate it. So now it's just gonna look at this PCB again, because now it matters which pin is in which side. Therefore, we know that PB8, PF0, PF1, PA0, and PA4 are on the same side, so I'll keep them on the same connector. PF1, PB8, and PA4. So just copy these guys, and I'll keep them on the same side. So that will help us in the PCB layout later. can keep this top one as ground, and then we have here the other pins. We have here pin 4 as well. Then we can keep VCC here at the bottom and keep ground again at the bottom, and 3.3 on this side. So we have this whole side populated. Now we go for the other side, which is the rest of the pins, which is PA10, PA9, PB1, PA7, PA6, and PA5. So just these three, just copy them, put them over here, like this. Actually, it would be better if I keep them below, like this. Then we have PB1, and then we have PA9 and PA10. PA9 and PA10. That's all on this side. And we have PA0, which is PA0, which is on the other side. So that should be on that side. I can get PA0, which is our HMLDT over there, and we can remove this guy on this. And now we have, I think we have populated all the pins except these two. PA4 is there, P5, P6, P7, P1, P8, P1, and P0. Everything is populated, so now just gonna keep this one another ground. And then after these connectors, I will put them aside. So selecting this, put them aside. I'll get 4 connectors. Four connectors, and I'll keep for the programming. So these 4 connectors, 2 wires will be 3.3 from the programmer STM link, and the other 2 will be these guys. You can name this box in headers / prog pins, programming pins. So that will be basically it. So now we have to find there's any mistake on our schematics by doing a ERC, which is electric use checker. Just run the ERC to show you that the reset pin is not connected. I'm showing the inputs not driven by any output, again on the same pin. And here is showing this. So to solve this too, just give power flag, because it's saying that the input is not being driven by anything. So just give a power flag here. So you determine that the power is coming from outside in plain terms over here. Then and now we have just the reset pin. So the reset pin is a pin which is supposed to be driven high when pressed, and it's supposed to be driven low when pressed. So therefore we need a push button, a pull up, and a capacitor if you need, but I just gotta give a push button and a pull up. So just go over here for switch, and you just put a switch. Sorry, something went wrong here. Yes, we go for switch underscore push, and put it over here, and then we get a resistor for pull up. So it means that whenever the button is not pressed, this switch will be always high, and this will be connected to our reset. And here let's connect to ground, and here we have to connect to 3.3. So now this guy doesn't have a footprint, so I'll find a footprint for it. Just find a simple footprint. To find the smallest one, yes, this one. Then if we run our rules checker again, we'll find no errors. So this will be all done for the schematics. So if you want to go all over again, here we have our input pins. This is our voltage, analog voltage input, where we put some set of decoupling capacitors to filter different frequencies or fluctuations. Here we have a decoupling capacitor for the VDD. This is a standard value that I use among my PCBs. And for the VDD, and we have our VSSA, which is our GND ground, connected to ground. Then we have the pinouts here of an MCU, which connected to several pinouts, and we have connected to our RS-485 lines, and the LED, built-in LED, which is over here, and here also for our output lines, GPIOs. And moving part to the RS-485, we have here resistance in parallel with the A and B lines of the RS-485, and we have here our UART lines for the RS-485. The transmit and receive data enable receive or enable transmit, along with the decoupling capacitor as well. And here we have our voltage regulation part, which we have a bulk capacitor, and then a smaller capacitor for filtering some some fluctuations, because in the MCUs we have the fine frequency filter, or I'll say decoupling capacitors in this. And again we have here another in the output of the voltage regulator, which is a simple AMS 1117 same set of capacitors, and a LED for power. And here we have our pin headers, 2.54 pitch pin headers. And that will be it for today's video. I hope you enjoyed it. And in the next video, we're going to get into the PCB part. Any doubts, leave it in the comment section. Thank you.